We're going to approach this example a little bit differently. Here we have a graph of a polynomial function. We identify that it has x-intercepts at -5 and at 2, and a y-intercept of -100. We see that the end behavior of the function has both parts of the function pointing downward on the left and on the right. If we wanted to write the function, an equation for the function, we need to use all of that information to produce the equation. The first thing that we should notice is that the x-intercepts give us two factors, the factor x plus 5 and the factor x minus 2. Because the function touches the x-axis at those 2 points and not crosses, that's a good indication that they are going to be at least squared. Remember our rule, if it has an even power, then we're going to touch at that root. In this case, we have touching at both of the roots, so they both need that even power. But this generic form of the function discounts one extra little feature, which is the need for an a. We saw in some of our previous examples that that scalar multiple has the effect of changing the y-intercept. It's not going to change the x-intercepts. Those are going to stay the same, but it will change the y-intercept. So we may need to adjust that number a in order to get -100 as our y-intercept. Because we know that it's a y-intercept, we know that its x-coordinate must be 0 and its y-coordinate must be -100. We can substitute those numbers into the function, and it will look like this. -100 equals a times 0 plus 5 squared and 0 minus 2 squared. 0 plus 5 is 5. 5 squared is 25. 0 minus 2 is -2. -2 squared is 4. And we're left with -100 equals 100a. And that, of course, means that a must be -1. That should make sense with what we understand about polynomials already. We were going to need something that forced the end behavior of this function to point downwards. If it was just left like this, and a was positive, we would anticipate, based on end behavior analysis, that the graph would point upwards, because this factor is creating an x squared term, this factor creates an x squared term, you multiply them together, we're looking at a polynomial that's x to the 4th. And in order for x to the 4th to be pointed down, we need that negative coefficient in the front. So the -1 that came from the a is doing a lot of that heavy lifting for us. So we end with a final version of the function, -1, which solves our both y-intercept and end behavior problem, a repeated root of -5, and a repeated root of 2.